Good day, everyone. I'm Justin Cervera, uh, Computer Engineering 4B. This is Digital Signal Processing for the Laboratory Activity 7, Event Symmetry Digital Signal. So the objectives are generate and plot signals even when with even symmetry using Python and to verify the even symmetry property numerically and graphically. So the background, a signal x of n is said to have even symmetry if x of negative n is equal to x of n. Examples are the discrete cosine wave and quadratic function. So for the procedure, we need a compiler with Python installed. I'm using a Visual Studio Code as a compiler. So first, of course, we need to import the required library, the NumPy and Matplotlib. NumPy as NP and Matplotlib as PLT. This statement here is for the array of numbers starting from negative 10 to 10 with steps of 1. This is the discrete time index, and we need to create the even symmetric signals. X of 1 is the cosine wave, np.cos. This generates the cosine wave function and the formula. This control or manipulates the frequency of how the signal or how it faster oscillates. And for the x of 2 equals n raised to the power of 2. So squaring, so this always makes the value positive. So both the left and right sides of the graph look identical for the plotting the signals. And to plot the cosine wave, even symmetry signal of cosine wave, the subplot 1, and this is to draw the discrete time signals. It will show in vertical lines, which is the stem, and K for the black base color, and for the title, and for the plot label X and Y to show the height of the plot, and the grid to make it easier to see the symmetry. Subplot 2, this is for the quadratic function. The graph will show a parabola shape of n raised to 2, which is same on both sides. And for the title and label, of course, and for the grid and the layout. The layout prevents the titles and labels from overlapping, and of course, to show the plot. Both plots, the cosine wave and quadratic function, will clearly show even symmetry, and this is to check the even symmetry mathematically. This reverses the arrays. For example, x of 1 is equal to 1, 2, and 3, and the np.flip will reverse it. So x of 1 is equal to 3 to 1. So these statements here will make reversed versions of the both signals, which we'll use to verify the symmetry rule. And to do these two statements here, the np.allClose, this checks if two arrays are almost equal. This also proves even symmetry. So if we run this code, we are given with two outputs, the cosine wave and the quadratic function. The cosine wave is perfectly mirrored, the positive and negative, and the quadratic function, a parabolic curve that is also symmetry on both sides, on the negative and the positive sides. So the outputs, this confirms the both signal, the cosine wave and quadratic function, satisfy the rule of the even symmetry signal. So after the procedure, the expected output is cosine wave and quadratic functions. Plots will show mirror symmetry. And for the guide questions and conclusion, in this activity, I used Python to create plot even symmetric signals like quadratic function and cosine wave. I think that's all for the laboratory 7, the even symmetry digital signal.